So I just want to acknowledge the students that have contributed, in particular to this, what I'm going to talk about today. So Sophia, I'm going to talk a little bit about Sophia's experiments today, later on. And Yuan, who finished last year and is working in industry, have basically done all the core work, I would say, a lot of the theory and numerical simulations in particular. And then there's a lot of people who have started recently. C and Romain are postdocs, and Sayed and Cornelius are also PhD students in my group. Right, so there we go. So what is a liquid-infused system? So basically, it is defined as a organization or organized fluid-fluid interfaces that are somehow locked in a material, right? And through capillary forces in particular. So a liquid-infused system consists of a solid scaffold, an infused liquid, and a working liquid. So here's an example in which I'm particularly going to focus on today is the simpler kind, which is a liquid-infused surface. And these things have been around now for a little bit over a decade. And there's actually quite a lot of studies and work done on these surfaces. So here we have a microstructure, for example, a solid with these sort of grooves, and there's an infused liquid here in green. And in this particular case, there's water above it, for example. So we can think of the infused liquid in this talk as some lubricant, for example, oil, and we can think of the working fluid in blue here as water. That's the easy way of thinking about this. Another type of liquid-infused system is a liquid-infused material, and this is something we introduced just recently. So it's a bit more complex. So here we have created fluid traps using a porous scaffold, and in these traps we can lock in this infused liquid here shown in blue, and we can get different shapes here. We have spherical shapes, but we can also get diamond-shaped, for example. So here again is the capillary forces that locks in these interfaces. And once we have these interfaces in place, we can use these materials and the system for a range of applications, right? So I'm not going to talk about liquid-infused materials today, but in this first paper that we published, we introduced a lot of different static applications, for example, using this as a composite material for actuation, or using this for encapsulating cells inside the droplets. And now we're moving more towards using liquid-infused materials when there is a flow going through the material. For example, you can imagine that you have these liquid interfaces and then you have a gas flow going through the material, and you can have reactions taking place at the interfaces, for example. For example, one thing we're looking into in particular is using these materials for CO2 capture, for example. So today I'm going to talk about liquid-infused surfaces. So I guess this is somehow related to porous media. I'm going to talk about in particular microstructures that are very simple, but a lot of the literature on liquid-infused surfaces are actually with porous materials, right? Right, and there's yes, so I can move on. So liquid-infused surfaces and liquid flows. So in particular, what we're going to focus on, and this is a little bit different what the majority of previous work has focused on, is when we submerge this liquid-infused surface below water or liquid that is flowing, right? So this is different from having these surfaces in air and using them for anti-repellent functionalities, for example, for repelling water or ice or condensation. So this is more looking into fluid from a fluid mechanics perspective. So there's two things I want to address in this talk. The first is, how do liquid-infused surfaces work when there's a liquid flow? And how does the lubricant behave in the flow? So in particular, the second point is something we have been working on. There's a complex interaction between the liquid flow and the liquid-liquid interface. And of course, there's a lot of work on this, as I mentioned before, in particular when it comes to fabricating the surfaces. So this is a rather big field in material science.
Excuse me for a moment of clarification. Are you talking about the same liquid infused and flowing, or are they two different fluids?
There are two different fluids, yeah.
Okay, so there's the surface.
So, yeah, so the green is one liquid and the blue is another liquid, yeah.
Thank you.
Think about the liquid, the green liquid as a lubricant, basically. Yeah.
Good, thanks.
Yeah, thank you for the question. So at the bottom, you see these references, and these are all reviews on the subject, and they focus primarily on fabrication techniques. How do you fabricate the surfaces? How do you tune the surface chemistry? How do you design the lubricant and so on? So there's a lot of surface chemistry and material science involved. And I'm not going to talk about that. I'm going to focus on the fluid mechanics aspects of these surfaces. So let's start with the first question. How do these surfaces work? So they have several properties. The first property is that these surfaces are slippery. And this is really a static property. It has nothing to do with the flow. So you have a liquid-liquid interface, and this is a slippery interface, and things don't get stuck, basically. For example, bacteria will not adhere to these surfaces because it's a liquid-liquid interface, basically. So there's a lot of work on this. For example, one of the first works that came out a decade ago, approximately, showed that these surfaces are actually extremely efficient in resisting bacterial settlement and biofilm growth, right? So here, I'm just showing you some extractions from this first paper by Epstein et al. From the group of Eisenberg in Harvard. So here in the black, basically, you see the surface of a liquid-infused surface where there's the fluorescent part is basically the bacteria. So you can see that there's basically zero bacteria after 7 days of growth condition on these surfaces. In contrast, if you have a super hydrophobic surface like a Teflon, or if you have a PEG surface, which is basically the state-of-the-art when it comes to surface chemistry for resisting bacterial settlement, you can see that there is much more bacterial settlement on these other type of surfaces. So this is one property of the surfaces, is that things don't get stuck on it, and in particular for bacteria. Another property is flow slippage. Now this is you need to have a fluid flow. So now the water in blue here is flowing from left to right, shown by the arrow. Now there will be a finite velocity at the interface, right? So there's a viscous flow, and that would generate a slip velocity at the interface. So you can see the velocity profile here, which is decaying as you get closer to the surface, but at the interface, it is not zero, right? So you have a slip velocity. You can also define the slip length. Basically, if you take this velocity profile, you assume it's linear and you extrapolate it to zero, then you can define this length scale, which we call slip length. And slip velocity and slip lengths are related to each other through what we call Navier slip boundary condition. So this is an important property of the surfaces, in particular, if you want to reduce drag, friction drag. So one of the first studies of this was by the group of Varanasi at MIT, and they did this at low Reynolds number. People have shown that this works also for turbulence and high Reynolds number. But here's a figure for low Reynolds number, and you have the viscosity ratio at the horizontal axis here. So the viscosity of water of the blue liquid over the infused lubricant, right? So as the viscosity ratio increases, so as the working liquid becomes more viscous, you can see that you can actually reduce drag, right? And you can get up to 16%. So the viscosity ratio, of course, is important, but due to this finite slip velocity, you can get this drag reduction. Now, a third property of the surfaces is a lubricant flow. So if we zoom into one of these textures and look at the liquid, which has been infused, the lubricant here, well, it starts to move, right? This is like a lid-driven cavity. So if you have a flow going from left to right, it will set in motion the lubricant. And this increases mixing, basically, which means that you can use these surfaces also to enhance heat and mass transfer from the surface. So, for example, if you imagine that you have a material which has a low heat conductivity, like PDMS, right? And you have lubricant, you can have an alkane, like hexane, for example. So the conductivities of the lubricant and the material are not too different, right? So we have 0.16 here watts per millikelvin, and here we have 0.2. So when we have such a systems, we can actually enhance heat transfer from the surface to the bulk, to the water significantly, up to 20%, because we create a mixing and a movement inside these cavities. So this is a third property of these surfaces. Right, so this is actually a rather short introduction to how the surfaces work and why they are interesting. So these are the properties that I just mentioned. We have the slippery part, we have the slippage, and we have the lubricant flow. And we can do a lot of things with these properties. So this is great. And these surfaces have, of course, show great potential for many applications. Now, there is, however, a few problems, and the problems are that the lubricant behaves in a lot of situations in an unpredictable way, right? So there's an interaction between the water and the oil or the lubricant that we don't really understand and we cannot really characterize fully yet. So the second part of this talk, which is going to be the bulk of the talk, is how does the lubricant behave in the flow, right? So I'm going to focus on a particular surface structure, which is very simple, basically. So it just grooves, streamwise grooves, as we can see here in gray. And again, this lubricant is shown in green. And so this is a particularly simple structure that we can control the geometry. We can perform analysis. We know everything about the geometry, and it sort of will carry over the fundamental understanding of these surfaces will carry over to more complex surfaces, for example, porous random surfaces, to some extent, of course. So some of the questions I want to ask is, okay, first of all, let's just set the stage here, what we want to look at. We can think of everything as in terms of forces. So the external flow, the water that flows over the surface will exert basically hydrodynamic stresses, right, on the lubricant and on the interface between the lubricant and the water. So what can happen is that the lubricant can resist these forces, in particular the deformation via surface tension, right? So these are basically capillary forces. In addition, we can also have dynamics on the interface itself if we have surface tension variations. So this will be a type of Maragoni stresses. So we have these forces, and really what we want to understand is how do these forces interact? When do they balance each other, and when do they not balance each other? And what happens if they don't, basically? So we're going to start with the simplest case, which is just the viscous shear stress, as you see in the direction of the grooves, shown here with the black arrow. And this has been studied by a group of Howard Stone in Princeton, Wexler experiment, we can call it. So what they did is that they looked at the microfluidic channel. So here in bottom in green, you have these grooves. And so this is a cross section. You don't see the actual solid. You just see the lubricant, which is silicone oil. And then they had a water flowing over these surfaces. And what is important also here is that there's a barrier at the downstream part of the channel. So basically, the lubricant, there's a reservoir you can think of the lubricant, right? So what they observed, so they looked at the mixed fluorescent particles into the lubricant and looked from the top with a camera. And this is what they observed. So the flow is going from left to right. And you can see that due to the viscous shear stress, tau xy, the lubricant gradually drains, right? So it's moving, the lubricant is, the grooves are getting emptied of the lubricant up to a point. And at some point, there's a retention of the lubricant, and there's a sort of a steady state reached, right? As you can see. So a large portion of the grooves are emptied of the lubricant, but not all of it. So,
excuse me, can I have a quick question?
Yes, absolutely.
What's the lubricant go?
Yes, the lubricant goes into a reservoir. So I have a big reservoir here. So the lubricant basically, so you can think of that the lubricant in the channels has a very much smaller volume than the reservoir, basically.
All right, thanks.
Yeah. So basically, we have this drainage, and the conclusion is that if there's a downstream barrier, so if there's a reservoir or a wall or whatever, the capillary forces can resist shear stress up to, not in the whole grooves, but part of the grooves will retain the lubricant, right? And we can call this part where the lubricant is retained, we can define this length as the retention length, and we call that L infinity. So this is what they did as an experiment, and they could also explain it. So they did use a confocal microscope to look at the cross-section of one of these grooves. So here is basically 50 grooves, right? So they took one of the grooves and they looked at the groove at the cross-section. So the lubricant here is in red. The interface between the lubricant and the water is in green. So if you look at the very downstream part of the groove, you see a flat interface, right? So this is just before the reservoir. If you look at further upstream of the groove, you see that there is a deflection of the interface. And this deflection is called delta. So you can see that there's a curvature of the interface upstream, but not downstream. But in particular, this is a sketch also from their paper. You can see that there is the shape of the interface changes in the downstream direction. So because of this change of the interface shape, you also have a Laplace pressure, right? So you will have a change of the Laplace pressure in the streamwise direction. So you have a pressure gradient, an adverse capillary pressure gradient, which can resist the shear stress, right? So you have a balance here between capillary force and the viscous shear stress. And they could do also do this force balance explicitly, and they came up with basically you can say a design rule that if your grooves have a length of L, which is smaller than L infinity, you will be able to retain the lubricant in your surface, right? So, and this L infinity is given by two ratios. So there's a ratio of K, which is the groove height, over the smallest curvature of the interface, which is at the very trailing edge or at the receding part of the lubricant, and also the ratio between the surface tension and the shear stress. So if you know these values, you can estimate L infinity, and then you can design your surface such that the grooves have a finite length, which is smaller than L infinity, and then you should be able to retain the oil in the grooves in the presence of shear stress, because there is a visco-capillary stress balance. Right. So we were fascinated by this, and we wanted to try this out. So we said, let's do it on a bigger scale. So we went and we use our water channel at KTH, which looks like this. This water channel is 3 meters long. It's a bit of a strange water channel. It's very long, but it's only 10 millimeters in height. So you have two walls that are 10 millimeters apart, but 3 meters long. So we can create a turbulent water flow, and at this test section downstream, we can flush mount lubricant infused surfaces, basically streamwise grooves, similar to what we saw in the macrofluidic experiment. And then we have optical access from above, and we can visualize the surfaces from the top by using fluorescent particles in a camera. And we can reach a few meters per second in the bulk velocity in this channel. So since the channel is very thin, but the velocity is very high, we get quite a high friction Reynolds number, right? So the bulk Reynolds number is somewhere between 4,000 and 40,000, but the friction Reynolds number can reach around 500 to 1,000 as well. So yeah, so it's a fully turbulent flow. So if we look at the lubricant now from above, we can see that after, it de-wets, so the dark regions are emptied of the lubricant. So you can see that gradually the grooves drain, and it gets darker and darker. And as we see, now let's see how long this movie is. I can fast forward a little bit. Eventually, we just get the fully drained surface, right? And this is no surprise. We just saw from the experiments of Wexler that you need to have barriers. You basically cannot have infinitely long grooves. So we have no barriers here. We just have streamwise grooves, which means that the viscous stress basically drains the surface out of all the lubricant. So at the end, there's nothing left. So this is according to Wexler's experiments. Now, what we did also a little bit by accident is that we also looked at drainage. We did the same experiment, but we changed the surface chemistry. So now this lubricant only partially wets the surface. So in the previous movie I showed you, if you put the lubricant inside the grooves, it will spontaneously invade the grooves. So it's energetically favorable for the lubricant to move to invade the grooves. So there's a positive spreading parameter, if you like, if you in terms of a wettability of the surface. In this case, which I'm going to show you now, I can play the movie. The lubricant only partially wets the groove. So if you place the lubricant inside the grooves, it will not spontaneously invade, right? So it's energetically favorable for the grooves to be wetted by the water instead of the lubricant. And of course, this is a bit strange, right? If you want to keep the lubricant in place, you will think that you would like to have a surface that likes the lubricant more than the water. But we did the opposite. So here is a surface that likes the water more than the lubricant. But what was surprising here, now we don't have any barriers. These are just very, very long grooves. But what was surprising to us was that after 2 hours, we reached a steady state, right? So if we have a partially wetting lubricant, we observe the steady state retention without barriers. And this is, of course, something different than Wexler's experiment. So here's a little bit of a more quantitative picture of the same thing just in the movies. So what you can see here in dark red is the total wetting list. So lubricant that spontaneously invades the grooves, right? And if you have a shear flow but no barriers, you get basically a fully drained surface, right? So after 2 hours, there's basically zero lubricant retained. Now, if you have a partially wetting lubricant, after 2 hours, you reach a steady state, and around 60% of the lubricant is retained in these grooves. So you have a finite retention of partially wetting lubricants. So we wanted to understand this, and I should probably move a little bit quicker here. So the lubricant in the groove here is shaped as a streak. So we extracted one of these lubricants, and we can see that there is a variation of the intensity here of the fluorescent images. So we can see that it looks a little bit, if we do a sketch, it looks a little bit like this, right? And when you look at this shape, you can see that there's an advancing contact angle and a receding contact angle, which we call theta R and theta A. And we obviously see there's also, again, a strong curvature of the liquid lubricant interface. So we have the same mechanism in terms of that there's a capillary pressure, which is varying in the streamwise direction, and is varying in such a way that it can resist the shear stress, right? But instead of the barrier, we have a pinning force. So basically, the lubricant is pinned here at the front edge, which means that you have a very high advancing contact angle. And due to a difference between the contact angles here, you get a different pressure between the front end and the back end, which creates an adverse pressure gradient, which resists the shear stress. And this is basically the same mechanism, this contact angle hysteresis, the same mechanism as you have when there's a drop on a windshield that can remain fixed even though there's gravity, right? So there's a difference in contact angles, which creates a Laplace pressure, which can resist gravity. So instead of gravity here, we have a lubricant droplet that can resist the shear stress. Right, so you can formalize this also analytically. You have the shear stress here in black. You have the pinning force here, which depends on the contact angle hysteresis, the surface tension, and the width of the channel of the groove. And you can balance these two, and you get a similar design rule as Wexler's, but now for partially wetting lubricants. So if you create finite grooves that are smaller than L infinity, which is related to what I just mentioned, contact line hysteresis and the ratio of surface tension to shear stress, you should be able to retain the lubricant. And yes, and this is just basically the same thing. We can skip that. And we did this. We created these finite cavities, and we could retain pretty much all the lubricant for partially wetting surfaces. So it's a little bit counterintuitive, is that you create a surface that dislikes the lubricant, but you can actually retain the lubricant there because there's a contact line hysteresis. Right. So I'm going to move on to another type of force that can be exerted from the flow onto the surfaces, and that's inertial forces, right? So we look at the viscous ones before, but you can also have forces that scales with the velocity squared. So what we call inertial forces. For example, a pressure at higher Reynolds numbers. So what we did here is that we used direct numerical simulations instead. So again, we have the surfaces that you recognize now, green and gray. And here I'm showing just isocontours of the flow field of the turbulent fluctuations just above the surface. So these are streamwise velocity fluctuations, positive and negative just above the surface. And so this is how a turbulent flow looks like. And of course, you have you don't have a constant shear stress now. You have varying shear stress, and you have wall normal velocity as well, which is not shown here. And you also have pressure fluctuations. So we also had periodic boundary conditions in our simulations, which we can just impose. So there's no drainage here, right? So we don't want to look at drainage. We just want to see how pressure fluctuations basically modify the surfaces. And we use a code, which is the finite volume solver. If you want to know more about it, I'm happy to tell you about that. So I'm going to very quickly just tell you about the configuration here. This is just a computational box. I'm not going to say much about this, except that there are two important parameters here. There's the Reynolds number, which is around 3,000, and the Weber number, right? So instead of the capillary number, which is the ratio of viscous stress to surface tension forces, we're looking now at Weber number, which is the ratio of inertial forces to surface tension forces. When we look at different Weber numbers, we want to understand the effect of inertia here. And typically, it's a quite low Reynolds number, but still fully turbulent. So you can imagine that we have a velocity of water of 1 meter per second in a channel, which is 0.5 centimeters in height. And the typical surface tension between oil and water around 50 millinewton per meter. Right, so when we set this up, we look at from top, we run a Weber number of 100, and we just look at it and we see this very nice, well-behaved lubricant, right? And we get a nice drag reduction. So we have flow slippage, we get a drag reduction. Now, if we increase the Weber number by a factor of 2, we actually get drag increase. So this means that the friction is actually higher now when we have a higher Weber number. And when we look at the surface in close, we saw waves. We saw these really large, modulations of this interface. And we of course, this is the reason why we lose drag reduction and get drag increase instead, is because these modulations act as surface roughness. So we took this red line, for example. If you look at the middle of one of these grooves, you can just look at the amplitude of the interface. So for Weber number 100, you have these waves. These are now different time instants, right? So you can see that is a traveling wave. Similarly, at Weber number 200, you have these traveling waves. The difference is in their amplitudes, right? So if you look at the vertical axis, you can see that for Weber number of 200, there is basically, these waves are 5 times larger than Weber number 100. So you can also look at the growth. You can look at the amplitude of these waves as a function of time. You can see that for Weber number 200, you have exponential growth for quite a long time. And then actually you get to significant amplitudes such that you get outside the viscous sublayer of the turbulent flow, which means that you get a roughness effect. So there seems to be a growth of waves here, and we wanted to understand that. So again, since we think that this is a really inertial forces, we look at the inviscid theory and use the linear stability theory to try to understand this problem better. So here again, you can see this sort of a cavity, the part of the groove, and there is now a wave on it. And we want to see if this wave grows or decays, right? So we can assume that we have a wave-like perturbation here, right? So this is a kind of an ansatz we can do, where we have a wave number in the streamwise direction, we have a wave number in the spanwise direction, and then we have the phase speed, a complex phase speed that will give us also the growth rate, right? So C is complex. And you can insert this into Navier-Stokes and you can linearize it. And if you neglect the viscous terms, you get the Rayleigh equation, right? So the Rayleigh equation governs the wall normal velocity perturbations V hat here, right? So if you solve this guy, you get the wall normal velocity perturbation. So the velocity in the fluid above the interface in the direction normal to the surface. And also it's important that you have linearized this around the basic state, which in this case is the turbulent mean velocity profile, right? K here is the wave number, kx plus kz squared. So we don't need to go into details. The point is that you get this equation, and then you can, from this equation, there's a corresponding pressure, right? You can always get the pressure out. And this is how the pressure looks like. So I'm showing you with the black arrow here. So P hat is the pressure from the fluid on the interface, right? So the question is, of course, how does the lubricant resist this, right? And again, is the Laplace pressure. So as the surface has been deformed, as the interface has been deformed, there will be a curvature and there will be a Laplace pressure. And, you know, as usual, we can write this Laplace pressure as surface tension multiplied by the curvature, which is basically the second derivative of eta, the amplitude of the interface, or the displacement of the interface. So we want to understand when these two can balance, when Laplace pressure can actually resist and fully balance the pressure fluctuations from the flow, and when it cannot do that. So I'm not going to go into details, but we solve this problem, and, you know, just to give you a little bit the big picture here is that you get, the bottom line is that the transfer of energy from the turbulent fluctuations to the lubricant is damped, so you don't get these perturbations to grow significantly when the width of the grooves, W here, normalized by the viscous length scale, is smaller than this expression. Now, this expression here in the parentheses is a Weber number, right? So it's a Weber number based on a friction velocity up to the power of -1/3. So we can write it cleanly like that. So we see here a constraint. So if we keep our grooves not too wide, right? So if we don't have too wide grooves, we will not have these capillary waves growing. But we can also imagine that we have a low surface tension. So if the surface tension is not too low, the limit, this Weber number, this critical value, will also will be higher, such that we also can avoid capillary waves. So there are two ways of making sure that you don't get these capillary waves. And we tested this. We have the Weber number here, Weber number hat here, and then we have the width of the grooves normalized with viscous length scale. And we have this 1/3 -1/3 asymptote here. And we can see that when the width is sufficiently low, or the Weber number is sufficiently low, we get drag reduction, these red triangles. But when we go above this sort of criterion, we get drag increase. We have the capillary waves. So this is inertial capillary balance, in contrast to visco-capillary balance that we saw before. Right, so how am I doing on time over Nick?
Yeah, we still maybe like 5 minutes, so that
5
we
minutes.
have some time for questions.
Okay, so if you guys give me 5 minutes, then that will be, then I can just go over the last part.
Mm-hmm.
Right, so the last part always, I always rush through this last part, but it's quite interesting. So, but I would try to keep it in below 5 minutes for sure. So one of the things we started to also try to look at is these interfaces. One of the big problems with the surfaces is that there's always something in the water that modifies the surface tension, right? So we want to understand how surface tension variations arise, and when they arise, how do they interact with the viscous shear stress? So, you know, surfactants are basically surfactant active particles. They have two parts, a hydrophilic part and a hydrophobic part, and they absorb at interfaces and they reduce surface tension. Right? So this is what we know about the surfactants from textbooks, is that the more of the surfactants you have, smaller of the surface tension you get, up to a point. Now, in a flow, if you have also shear stress, there's more that happens, right? It's not only a reduction of surface tension, you also get Maragoni stresses, right? So if you look at this lubricant, you can see that these surfactants, they have a inhomogeneous distribution, right? So you have more surfactants out at the stagnation point compared to the upstream part. So because you have then you will have a surface tension variation, and this surface tension variation will create a Maragoni stress. And this Maragoni stress or force acts in the opposite direction to the flow. And this has consequences. So I'm going to skip this part. This has consequences because it reduces significantly the flow slippage. Remember that flow slippage is something we want for drag reduction and also other functions. But if you have surfactants, you actually can completely kill and remove the flow slippage. And we showed this for both water, air, so this will be some sort of super hydrophobic surfaces, and water, dodecane and alkane here surface. So if you have extremely small amounts of surfactant concentration in the bulk, it should be bulk here, not build. In the bulk, for example, if you have a concentration of 10 to the minus 4, for example, here, your slippage is reduced by a factor of 2, right? So very small trace amounts of surfactants in the water can get absorbed at the interface and reduce the surface, the flow slippage. And we can also derive criterions for this and do the balance of forces, but I'm not going to talk about that today. I feel like that's going to be one thing too much. So let me just summarize this. So how do liquid-infused surfaces in liquid flows work? We've been mentioning, I gave you a small introduction that we can do a lot of things with these surfaces. They have many interesting properties. And in addition to these things that I mentioned, there's actually more, which I haven't talked about. But the price we have to pay when we work with the surfaces is that, you know, the good thing is that we have a lot of degrees of freedom. We have surface texture, we have surface chemistry, and we have lubricant, the lubricant which you can design. But we also have a dynamic surface, right, which actually is moving and has a lot of physics. So one of the things, a few things that I have talked about is that we can reach a viscous-capillary balance. We can avoid drainage by tuning the pore length, right? So we can do this for both partially wetting and totally wetting lubricants. We can make sure that the lubricant stays in place, although it wants to basically be drained. We can also tune the pore width in the other direction to achieve inertial-capillary balance, to avoid waves. And something I didn't talk about much about today at the last part is that we can also tune the geometry to have very fast kinetics, adsorption and desorption of surfactants to avoid slippage reduction. So these are some of the things we have learned, but there's much more, of course, of the surfaces which we're continuing to look into. So what I've talked about today can be found in these papers. 2 of them are published and 1 of them is in preparation. So just 2 more slides. I want to thank the whole group. I mentioned a few persons that have contributed to this work, but there's a few more people in the group that obviously create the environment that is really great, and I would like to thank them. And also the funding agencies here, which is all of them are Swedish funding agencies. And just one last slide. is that we're just kicking off an ERC project on liquid-infused surfaces and lubricant-infused materials in general. And the focus of loop flow is to continue some of the work we discussed now, but going deeper into this phenomenon. So if you want to know more about ERC, this ERC project, don't hesitate to contact me, and I'm happy to tell you more about that. Right, I think I will pause there, and so there's some time for discussion. Thank you.